Calculate the pH of acid, and now we're working with acid-base equilibrium. So we're working with weak acids and weak bases. So here's our first question. Calculate the expected pH of a 1.00 molar acetic acid, which is CH3COOH, and the Ka for this one is 1.8 times 10 to the negative 5. By the time we're done with this, you are going to have memorized that because you're going to use it so many times. For any acid-base equation, equilibrium, you should write the equation. That's a very good habit to get into. It's just a good idea, okay, because it really helps to set up the ice tables, okay. So your initial concentration for the acetic acid is 1.00. Initial concentration for the acetate ion is 0 and hydronium ion is 0. The change as it goes on is that the acetic acid will dissociate, and then you will also get a little bit of acetate, and you will also get hydronium ion. At equilibrium, you should have then 1.00 minus X, and then X and X for the product. So then we set up our Ka, which is 1.8 times 10 to the negative 5, and this is equal to X times X, and then all this is divided by 1.00 minus X, okay, because this is actually, let me write that out for you, the hydronium ion concentration, the acetate ion concentration, and then this is the acetic acid concentration, okay, that you need. So that's how you set this up. We're going to go ahead and ignore X over here, and we can ignore X because it's small, so it's meaningless right now. And I'm going to explain to you how and when to ignore X, okay, in our lives, because otherwise your calculations will become too complicated. So then 1.8 times 10 to the negative 5 is equal to X squared over 1.00, which you can ignore the 1, of course, and then you will take square root of both sides, okay, so which means something like this. And then once you do that, X turns out to be 4.2 times 10 to the negative 3. And so then the pH is going to be the negative log of 4.2 times 10 to the negative 3. Don't forget, 4.2 times 10 to the negative 3 is X, and X is also our hydronium ion concentration. So then our pH is 2.38. That's the final answer then for this. Okay, so ignoring X, there are two ways to do this, okay. So the first way, okay, of ignoring X is look at the dissociation, okay. So dissociation, if dissociation of X is less than 5% of molarity of acid, then you can ignore it, okay. So which means that 5% of 1 molar, which is then equal to 0.05, which means that you need to know the value of X. So X here is 4.2 times 10 to the negative 3. Now if you had not calculated X, you would not know what to do, okay. So which means you have to finish your calculation, and then if it turns out that X is actually more than 5%, then you have to do the calculation again, okay. So this is not the best way to do it. So this is what it means, okay. If less than 5%, then ignore, which, you know, 4.2 times 10 to the negative 3 is less than 5%. So because 5% would be 0.05 of the dissociation. So that's one way of doing it. I like the other way better because this is a little bit more straightforward, and it also doesn't make you do the calculation, all right. So then in the B, what you do, or in the second way, what you do is use the molarity of the acid and divide it by the Ka of the acid, okay. If it is more than 100, then ignore X, all right. More than 100 meaning that you're working in the third decimal place, third or fourth decimal place, and you know that's not going to make a huge dent in your pH or calculations, all right. So for example, in this case, the molarity of the acid is 1.00 and the Ka is 1.8 times 10 to the negative 5. And if you do the calculation, you'll turn out to be more than 100, way more than 100, because once you bring the 10 to the negative 5 up, it's going to be 10 to the power of 5 at least, if not 4 then, okay? But even that, it shows that it's much, much greater than 100, so then you can ignore x. And I like this method a little bit better because you don't have to calculate the value of x. You can figure it out right away whether you need to calculate or go on to ignore x or not.